In this video, I'd like to talk about an application of the derivative called L'Hopital's rule. All the way back when we first introduced the derivative as a difference quotient, we used limits to calculate derivatives. But what we're going to do in this section is use derivatives to calculate limits. Now this rule is a little bit tricky. So first we're going to practice using it, and then we're going to examine some incorrect uses of it. The setting is this. So we're considering taking the limit of a fraction. For example, the limit as x approaches infinity of the fraction x divided by natural log of x. Now there are numerous imprecise ways to answer this question, non-computational methods. For example, we could graph this function and we could look at what the graph is doing. We could plug in very large values of x and see what the function is doing in that situation. But as usual, let's see if we can get an exact or computational method that might be a little bit more conducive to, for example, programming and automation. L'Hopital's rule says that if you want to find the limit of a quotient, something like the limit as x approaches a number a of f of x divided by g of x, the first thing that you need to do is you need to check to see if L'Hopital's rule can actually be used to answer that question. Now, in order to be able to use L'Hopital's rule, one of the following two conditions has to be satisfied. The first condition that could be satisfied is that the limit of the numerator, f of x by itself, and the limit of the denominator, g of x by itself, both exist and equal 0. Now, if that is not the case, if one of your limits is not 0, then not all hope is lost. Another possibility is that the limits are both positive or negative infinity. Okay, now you've checked your individual numerator and denominator out, and you found that either both the numerator and denominator approach 0, or both the numerator and the denominator approach plus or minus infinity. If either of those conditions is satisfied, then you can calculate the limit of the quotient by calculating the limit of the quotient of f prime divided by g prime. To see the benefit of being able to do this, let's go back to this running example. And the first thing that we need to do is we need to investigate the limit of the numerator and the denominator individually. In order to have a chance of using L'Hopital's rule, we need to make sure that, in some sense, both of these limits match, that both the numerator and the denominator are approaching 0, or they are both approaching positive or negative infinity. Now in this case, as x goes to infinity, x goes to infinity, and the same thing is true for the natural log of x. So in this case, L'Hopital's rule can be used, and it says that instead of calculating the limit of the original quotient, you can instead calculate the limit of the derivatives of these two functions. The derivative of x equals 1. The derivative of natural log of x equals 1 divided by x. So if we simplify this, we get the limit as x approaches infinity of x, which, as we know, is definitely going to be positive infinity. See another example of L'Hopital's rule in this exercise. In this case, we're looking at the limit as x approaches 0 of cosine of x minus 1 all over x squared. Now both of these functions are continuous at x equals 0, so we can find these individual limits just by plugging 0 into the individual functions. So on the left-hand side, this would be cosine of 0, take away 1, which would be 1 minus 1, which would be 0. And on the right-hand side, the limit is of x squared would be 0 squared, which would also be 0. So in this case, the two limits do match, but this time both of them are 0 instead. So now, L'Hopital's rule says that if you want the limit as x approaches 0 of cosine x minus 1 all over x squared, you can calculate the limit as x approaches 0 of the derivatives of these functions. So the derivative of the numerator becomes negative sine x, and the derivative of the denominator becomes 2 times x. But what's interesting about this is that we have once again arrived at a quotient where the numerator and the denominator are both individually approaching 0. Negative sine approaches 0, 2x approaches 0, and what this means is we can use L'Hopital's rule a second time. So using L'Hopital's rule a second time, we can turn this into the limit as x approaches 0 of the derivative of negative sine x, which is negative cosine of x, divided by the derivative of 2x, which is 2. So now, having used L'Hopital's rule 2 times, we've finally arrived upon a fraction which is continuous at x equals 0. So we can find the value of this limit by simply plugging 0 into the function to get cos 0 divided by 2, which is negative 1/2. Now this is a rather unique example, and this is a limit that I want you to remember, especially if you're planning to take Calc 3. Let's calculate the limit as n approaches infinity of the nth root of n itself. So what I'm going to try and do is rewrite the function in this problem so that it has the format function divided by another function. And one of the main tools that I'm going to use in order to do that rewrite is the fact that an nth root is equivalent to an exponent of 1 divided by n. This is the number that I'm trying to find, so I'm going to just nickname this by L. So here's the fraction that I'm kind of looking for, but currently there is a problem. Currently the fraction that I am looking for is in an exponent. So what tool do we have for getting things out of an exponent? The tool that we have is given by the natural logarithm. So I'm going to take the limit not of n to the power 1 over n, but of the natural log of n to the power 1 over n. But you can't just apply the natural log to one side of the equation. This is going to apply natural log to the end result as well. Okay, so now let's try and simplify this expression on the left side. We're now calculating the limit as n approaches infinity of, bring the exponent down, this is 1 over n times the natural log of n. So here's our fraction. We're looking for the limit as n approaches infinity of natural log of n divided by n. Now notice that as n approaches infinity, both the numerator and the denominator individually go to infinity. So that means L'Hopital's rule can be applied. This is the same thing as the limit as n approaches infinity of 1 over n divided by 1. So as n goes to infinity, 1 over n goes to 0. 0 divided by 1 is still 0. And so the natural log of the limit that I'm trying to find is equal to 0. So what, therefore, is L? What is the value of the limit that I'm actually trying to find? L must be equal to e to the power 0, must be equal to 1. And hence, the limit as n approaches infinity of the nth root of n is equal to the number 1. Now, let's study some common incorrect uses of L'Hopital's rule. For example, someone is considering calculating the limit as x approaches 0 of x squared plus 1 divided by 3x plus 4. So they say, oh, okay, that must be the limit as x approaches 0 of the derivatives. The derivative of the numerator is 2x. The derivative of the denominator is 3. So if I stick 0 into that, then I get 0 over 3. I get 0. This is not correct. And the problem is that they were not in the position to use L'Hopital's rule in the first place. If I look at the limits of the individual numerator and denominator, then the individual numerator and denominator are approaching 1 and 4 respectively as x goes to 0. So not only is L'Hopital's rule not appropriate for this situation, it's kind of overkill in this situation, because this function is already continuous at x equals 0, and you can just plug 0 right in. Here's another situation where folks can easily get mixed up. Find the derivative of the function 2x divided by sine x. Someone looking at this might decide that they're going to take the derivative of the numerator and the denominator separately. Maybe this will give them the derivative of the entire fraction. But this is definitely incorrect. They're trying to use a L'Hopital's rule idea, but this isn't a L'Hopital's rule problem, because we're not being asked to calculate a limit. We're being asked to calculate a derivative of a quotient. And for derivatives of quotients, not limits of quotients, we need quotient rule. The quotient rule, as we know, rather consistently gives us a big mess for the value of f prime. The derivative of the quotient in this problem would be given by the bottom function sine of x, times the derivative of the top function minus the top function times the derivative of the bottom, all over the bottom squared. So this would be equal to the derivative of 2x over sine x. L'Hopital's rule is for limits only. That concludes today's material. We introduced a rule called L'Hopital's rule, which in certain situations allowed us to calculate a limit of a fraction by taking the derivatives of the numerator and the denominator.